Across the immense, cold fabric of spacetime, there stretches a finite volume of awareness, a sphere centered not on any privileged point in the cosmos, but on the observer. This is the observable universe, a bubble of light and information whose boundary is defined by the finite speed of light and the 138 billion years that have elapsed since the cosmos began its expansion. Its diameter is estimated at a staggering 93 billion light-years, a distance so far beyond human intuition that it renders all terrestrial comparisons meaningless. Within this unfathomable expanse, light from the most ancient events has just now completed its journey to our instruments, painting a picture of the universe not as it is, but as it was, layer by layer, through the depths of cosmic time. To begin to comprehend the contents of this volume, one must not look toward the brightest and nearest celestial landmarks, but rather toward the blackest, most unassuming patches of the night sky. In the constellation Fornax, there lies one such region, a tiny sliver of darkness covering an area merely 1/13 of the entire celestial sphere, equivalent to the size of a grain of sand held at arm's length. For centuries, this patch was nothing more than negative space, a void between the stars. Yet, it was here that humanity aimed its most powerful eye, the Hubble Space Telescope, not for a fleeting glimpse, but for a prolonged, unwavering stare. The result of this vigil, the Hubble Ultradeep Field, became one of the most profound images ever captured, a core sample drilled through billions of years of cosmic history. It revealed not emptiness, but a tapestry of nearly 10,000 distinct points of light, each one not a star, but an entire galaxy. The implicit question that bloomed from this single, deep look was not just what these lights were, but how many more lay beyond them, across the whole of the sky, hidden in every direction within the silent, pervasive darkness. The creation of such an image was an act of extreme patience, a technological meditation conducted in the vacuum of space. The Hubble Space Telescope, a marvel of engineering orbiting 540 kilometers above the Earth, had to hold its gaze fixed on that minuscule spot with unimaginable precision. For hundreds of orbits, accumulating over 1 million seconds of exposure time, its instruments gathered the most ancient photons in existence. These were not a flood of light, but a delicate, intermittent rain of individual light particles, some of which had been traveling for over 13 billion years, their journey beginning when the universe itself was a mere infant, less than 5% of its current age. Each photon, upon arriving at Hubble's 24-meter primary mirror, was a messenger from a bygone epoch. The light was collected by the advanced camera for surveys and the near-infrared camera and multi-object spectrometer, detectors cooled to cryogenic temperatures to minimize their own thermal noise, allowing them to register the faintest whispers from the cosmic dawn. The telescope's gyroscopes and fine guidance sensors worked in concert, compensating for the slightest tremor, ensuring that each incoming photon from a distant galaxy landed on the same pixel of the detector, orbit after orbit, day after day. The final image was not a single snapshot but a composite, a digital stacking of hundreds of separate exposures, painstakingly cleaned of cosmic ray strikes, satellite trails, and instrument artifacts. What emerged was a portrait of cosmic density, a field teeming with spirals, ellipticals, and strange, irregular blotches of light. The image was a direct refutation of emptiness, a confirmation that the universe, on its grandest scales, leaves no space truly vacant. It was a statistical sample, a representative cross-section of the cosmic population, offering the first empirical foundation upon which to build a census of the heavens. To interpret this deep field, to translate its points of light into a meaningful cosmic map, requires an understanding of the very nature of an expanding universe. The light from these distant galaxies does not travel through a static, empty void, it journeys through the dynamic medium of spacetime itself, which has been stretching continuously since the Big Bang. As spacetime expands, it stretches the wavelengths of the photons moving through it, a phenomenon known as cosmological redshift. A photon emitted in the blue or ultraviolet part of the spectrum from a nascent galaxy billions of years ago will have its wavelength elongated over its immense journey, arriving at our telescopes today as a red or even infrared photon. The amount of this shift, the redshift value, is therefore not a measure of velocity through space, but a direct indicator of the expansion of space itself and, by extension, a proxy for both distance and time. The faintest, reddest smudges in the Hubble ultradeep field are the most distant and ancient objects, their light shifted so dramatically that they are visible only at the edge of the infrared spectrum. Astronomers can analyze the light from each galaxy, breaking it down into its constituent spectrum and identifying the characteristic absorption or emission lines of elements like hydrogen. By comparing the observed wavelength of these lines to their known wavelength in a laboratory on Earth, they can calculate the galaxy's redshift with high precision. This turns the two-dimensional image into a three-dimensional model, with redshift providing the crucial depth axis. We are not merely looking at a flat projection of the sky, we are looking down a temporal tunnel, where nearby, fully formed galaxies give way to progressively younger, smaller, and more chaotic structures, until we are peering at galaxies as they were when the universe was only 800 million years old. The redshift is the cosmic yardstick, the tool that allows us to sort the 10,000 lights of the deep field into their proper chronological and spatial order. With a meticulously catalogued sample of galaxies from a tiny, representative patch of the sky, the process of extrapolation can begin. This grand leap of calculation rests upon a foundational concept in modern cosmology, the cosmological principle. This principle asserts that, when viewed on sufficiently large scales, the universe is both homogeneous, meaning it has a uniform density and structure everywhere, and isotropic, meaning it looks the same in every direction. There are no special places, no cosmic center or edge. Our location is not privileged, and the patch of sky chosen for the ultradeep field is not unique. If this principle holds true, then the density of galaxies observed in that one small window should be, on average, the same as the density of galaxies in any other window of the same size, anywhere in the sky. The calculation, then, becomes a matter of cosmic arithmetic. The Hubble ultradeep field covers an angular area of approximately 11 square arc-minutes. The entire celestial sphere spans about 1485 million square arc-minutes. By dividing the total area of the sky by the area of the deep field, one finds that it would take roughly 13 million such fields to tile the entire cosmos. If our one field contains approximately 10,000 galaxies, then a simple multiplication suggests a universe populated by something on the order of 130 billion galaxies. This number, derived in the early 2000s, was a landmark estimate, providing a tangible, albeit mind-boggling, figure for the galactic population of our observable sphere. It painted a picture of a universe crowded with immense stellar cities, each containing hundreds of billions of stars, separated by millions of light-years of intergalactic space. For a time, this figure, between 100 and 200 billion galaxies, stood as the canonical answer, a testament to the power of a single, deep observation. However, this initial census carried a profound and acknowledged limitation, a bias inherent in the very act of observation. A telescope, no matter how powerful, is a light-collecting bucket. It can only detect objects whose brightness exceeds a certain threshold. The Hubble ultradeep field, for all its depth, could only register galaxies that were luminous enough, or close enough, for their faint light to be distinguished from the background noise of the cosmos and the instrument itself. This meant that an entire population of galaxies likely remained invisible, their light too feeble to be captured. Cosmologists understood that galaxies, like stars, are not all created equal. They follow what is known as a luminosity function, a statistical distribution describing how many galaxies exist at each level of brightness. This function shows that for every one large, bright galaxy like our own Milky Way, there are many more small, faint dwarf galaxies. These dim stellar systems, containing perhaps only a few million or a billion stars, are far more common than their larger brethren, but their low surface brightness makes them extraordinarily difficult to detect, especially at cosmological distances. The 100 billion galaxy estimate was based almost entirely on the brighter, more easily seen members of the cosmic population. It was akin to conducting a census of a continent's population by only counting the people living in its major cities, while ignoring the vast numbers dwelling in small towns, villages, and remote rural areas. The true number of galaxies had to be significantly higher, but determining how much higher required moving beyond direct observation and into the realm of sophisticated modeling to account for the vast, unseen majority. To probe this hidden universe of faint galaxies, astrophysicists turned to the immense power of computational simulation. They began to construct virtual universes inside supercomputers, digital laboratories where the fundamental laws of physics could be applied to initial conditions mimicking those of the early cosmos. These simulations, such as the illustrious TNG or Eagle projects, start with a large, cubic volume of expanding space, seeded with a mixture of dark matter, dark energy, and ordinary baryonic matter, the hydrogen and helium gas from which stars and galaxies are made. The initial distribution of this matter is not perfectly uniform. It contains the minuscule density fluctuations observed in the cosmic microwave background radiation, the fossil light from the Big Bang. With these starting conditions set, the simulation is set in motion. The code calculates the gravitational force between billions of discrete particles, advancing cosmic time in small increments. Over billions of simulated years, gravity, the master architect of the cosmos, begins its work. The slightly denser regions of dark matter begin to pull in more matter, their gravitational influence growing stronger in a runaway process known as gravitational instability. This invisible scaffolding of dark matter collapses into a vast, intricate network of filaments and nodes, a cosmic web that dictates the large-scale structure of the universe. The ordinary gas, feeling the gravitational pull of the dark matter, is drawn into these filaments, where it cools, condenses, and collapses under its own weight to ignite the first generations of stars. These simulations show the birth of galaxies not as singular events, but as a continuous process of accretion and merger within the dense corridors of the cosmic web. Crucially, the models predicted that this process would create a profusion of small, low-mass dark matter halos, each capable of hosting a dwarf galaxy. When the simulated universes were observed with virtual telescopes that mimicked Hubble's detection limits, they produced deep fields that looked remarkably similar to the real one. But when the simulators counted all the galaxies that had formed, including those too faint for the virtual telescope to see, the number was vastly greater. These simulations, combined with a reanalysis of observational data and theoretical models of galaxy formation, led to a dramatic upward revision of the cosmic census. In 2016, a new study integrated deep field observations with models of the galaxy luminosity function, pushing the analysis further back in time than ever before. The researchers concluded that for our current telescopes to see the 10,000 galaxies in the ultra-deep field, there must be at least 10 times as many galaxies in that same volume of space that are too small, too faint, and too distant for us to detect. When this new, more complete understanding of the galactic population was extrapolated across the entire sky, the estimated number of galaxies within the observable universe swelled to a new, almost incomprehensible figure, 2 trillion. This revised number does not invalidate the earlier observations, it enriches them, placing them in a broader context. The universe is not just filled with the grand, luminous spirals and ellipticals that dominate our images. It is overwhelmingly populated by a sea of faint, unassuming dwarf galaxies. But this new number also introduced a profound temporal dynamic. The models indicated that the density of galaxies was not constant throughout cosmic history. In the distant past, when the universe was younger and smaller, galaxies were much more numerous. The 2 trillion figure is not just a census of the present, but an integrated count across cosmic time, reflecting an era of galactic assembly. The universe of the past was a frenetic place, filled with a swarm of small proto-galaxies, constantly colliding and merging. The grand galaxies we see today are not primordial, they are the consolidated products of this violent, ancient history. This understanding recasts the history of the cosmos as an ongoing process of hierarchical structure formation, an era of assembly that is still underway. The 2 trillion galaxies did not all spring into existence at once. The first were small, irregular collections of gas and stars, born from the primordial density fluctuations just a few 100 million years after the Big Bang. These proto-galactic fragments, numbering far more than 2 trillion, served as the building blocks for everything that would follow. Over the subsequent eons, gravity orchestrated a cosmic ballet of mergers and acquisitions. Smaller galaxies were gravitationally captured and cannibalized by larger ones, their stars and gas stripped away and incorporated into the growing structure of their conqueror. The Milky Way's own halo is filled with the faint stellar streams of dwarf galaxies it has consumed over its lifetime, ghostly trails of its past meals. This process of merging is not a relic of the distant past, it is happening now. The Andromeda Galaxy, our largest neighbor, is currently on a collision course with the Milky Way, destined to merge in about 45 billion years to form a single, larger elliptical galaxy, colloquially dubbed Milkomeda. Therefore, the number of galaxies in the universe is not a static quantity. It was highest in the distant past and has been steadily decreasing ever since. The 2 trillion figure represents an average over the volume of the observable universe, a volume that encompasses both the present and the deep past. We are living in an epoch of cosmic consolidation, where the myriad small systems of the early universe are gradually being forged into a smaller number of more massive, more complex galaxies. The galactic population is declining, not through extinction, but through union. Zooming out from the individual lives of galaxies, one can perceive the grand architecture that organizes them. These 2 trillion stellar systems are not scattered randomly throughout space like dust motes in a sunbeam. They are arranged in a breathtakingly vast and intricate pattern known as the cosmic web. This structure, first predicted by simulations and now confirmed by massive galaxy redshift surveys, is the largest known pattern in the universe. It is a sponge-like network of immense filaments of dark matter and gas, stretching for hundreds of millions of light-years, connecting dense hubs and surrounding vast, nearly empty regions called cosmic voids. The galaxies themselves are like luminous beads of dew, condensed along these invisible threads. They trace the underlying skeleton of dark matter, making its structure visible to our telescopes. Where the filaments intersect, gravity's pull is strongest, and here we find the great galaxy clusters, cosmic metropolises containing thousands of individual galaxies bound together in a deep gravitational well, all swimming in a sea of superheated, X-ray emitting gas. Our own Milky Way resides in a more sparsely populated region, a filament on the outskirts of the Virgo cluster, which itself is part of the even larger Laniakea supercluster. In stark contrast to these dense structures are the voids, immense bubbles of underdensity that can span hundreds of millions of light-years. These are the great deserts of the cosmos, where the expansion of the universe has swept matter away, leaving behind a profound emptiness, punctuated by only the occasional, lonely galaxy. The existence of 2 trillion galaxies is therefore only part of the story. Their arrangement into this magnificent, web-like tapestry reveals the fundamental role of gravity and dark matter in shaping the universe on its grandest scales. The cosmic web is the context, the environment that governs the birth, life, and death of every galaxy within it. Finally, any discussion of the total number of galaxies must confront the ultimate boundary, the edge of observation itself. The 93 billion light-year diameter of the observable universe is not a physical wall or a material edge of the cosmos. It is a horizon of information, a conceptual boundary called the particle horizon. Since the universe is 138 billion years old, light from any object more than 138 billion light-years away has simply not had enough time to reach us. In fact, due to the continuous expansion of space during that light's journey, the objects whose light is just now reaching us are currently located much farther away, at a comoving distance of about 465 billion light-years, defining the radius of our observable sphere. What lies beyond this horizon is, by definition, unknowable through any direct observation. There is no theoretical reason to assume the universe ends where our view does. On the contrary, our best cosmological models, particularly the theory of cosmic inflation, suggest that the universe as a whole is vastly larger than the portion we can see. It may even be infinite. If the universe beyond our horizon is similar in character to the part within it, a reasonable assumption based on the cosmological principle, then the total number of galaxies in existence could be functionally infinite. The 2 trillion galaxies of our census are merely the inhabitants of our local, visible patch. It is as if we are on a ship in the middle of a vast ocean, able to see only to the horizon. We can count the waves within our circle of sight and extrapolate the nature of the sea, but we have no direct knowledge of what shores, islands, or other ships might lie beyond that circular limit. The 2 trillion galaxies, then, represent a lower bound, the number contained within our cosmic bubble of awareness. It is a profound acknowledgement of our epistemic limits, a number that is simultaneously a measure of the universe's richness and a testament to our own confined perspective within it. The true cosmos, in its full and complete totality, remains a realm of theoretical inference and philosophical contemplation, its scale likely dwarfing even the staggering numbers we can empirically derive. The answer to how many galaxies exist is ultimately bifurcated: 2 trillion that we can, in principle, account for, and an unknown, possibly infinite, number that remain forever beyond our reach, their light lost to the eternal expansion of spacetime.